prep. Let's get started on another video series. For our scope and sequence, this is the 8th unit in the course. This really is, we're right there at the end of the Calculus 1 curriculum. This is where we look at area bounded by 2 or more curves. We look at volumes of revolution, and we look at volumes of solids with known cross sections. So let's kind of jump into this. Actually, before we look at this problem, let's have a little background conversation. Earlier in the course, we looked at the definite integral. So when I say definite integral of f of x dx from some point A to some point B, I would expect at this point, you know that whatever the function happens to look like, here's f of x, here's the vertical line x equals a, here's the vertical line x equals b, the definite integral is going to determine how much area is there between f of x and the x-axis. That's what we've looked at so far. Sometimes our area winds up dipping below the x-axis, in which case we have a negative area. In some cases, we actually have maybe 2 functions that are coming together. Let's let the purple-pink one here be f of x. The one in black here is g of x. We've looked at some problems where I want to find this area in the first quadrant, and we know at this point that I actually would need to have 2 different integrals. If this is, we're only interested in the first quadrant, we would start at x equals 0. Let's call this point over here x equals a, and this point over here x equals b. I would expect at this point in the course that, you know, if you want this area in black, well, first of all, I have to find how much area is there from 0 to a. Well, what's the function? The function that forms the boundary here is f of x. Okay, so that gives you this first area from 0 all the way to a. But how about the last piece? Well, now I need another integral. I'm going to integrate from a to b, and the function I'm going to integrate is g of x dx. This is background knowledge I expect you have before watching this video. If you're not comfortable with this, I would recommend you actually maybe pause this video, set it aside, and go back to one of the earlier videos on the definite integral and accumulation. But with that assumption in place, let's move on. So this first question we're going to look at, we have a region R shown below. If I haven't said so yet, this is a calculator active question. It's bounded by 3 curves. We have f of x is arc cosine. Now, if you don't remember exactly what arc cosine looks like, don't worry. This is something that you are going to graph on your calculator. We have the function g of x equals 10x squared minus 2. That's a parabola. We have h of x equals 2 to the x plus 1. So that's exponential. I want to add some color to this diagram. Let's see, I know for sure that g of x is a parabola, so that must be this pinkish purple one over here. So that's g of x. I'm also pretty confident that I know what the graph of an exponential function looks like. That'll be the light blue. Here we go. That's exponential, that's h of x. So it must be that the arc cosine graph, f of x, is, as well, do an orange, that's this guy over here. What I'm going to ask you to do is, before we actually do anything else with this problem, let's take a moment, graph it on the calculator, make sure you are coming up with a good viewing window. Let's make sure that your graph matches mine. I'm going to type all this into my calculator. So, you may not be able to see my calculator screen too clearly, but don't worry. Everything I type over here, I'll transfer to the graph. So we've got 3 functions that we're considering. We have arc cosine of x, so that's second cosine on your calculator. We have 10x squared minus 2. We have 2 to the x plus 1. 2 to the x plus 1. There it is. Okay, when I graph it, you probably cannot see it at all. So I'm going to take that off the screen. When I graph it, I actually don't have a very good window, so I'm going to change my window. Let's see, let me just do zoom 6 so I get a nice standard window. Well, that seems a little bit too small, so I want to spread my window out. Maybe I will use x min as -3, x max as +3. Okay, that seems to be a little bit better. Yeah, I can work with that. Well, if I want to find the total area bounded by all three, region R is this shape over here. That's what's being shaded in. Let's start over here on the far left. I need to know where to start. Where I'm going to start my integration, I'm going to call this point A. A is the intersection of the parabola and the exponential curve. So on my calculator, I'm going to go and I'm going to use the second calc feature. I want an intersection, and I want an intersection of arc cosine and, I'm sorry, not arc cosine. I want the intersection of, let's see, we have the parabola. So that's the second one that I've graphed. So we need y2. And we need the third function, which is 2 to the x plus 1. And when I find that intersection point, I see that A is approximately -0.6047787. Make sure that you're getting that as the x coordinate for the intersection point there. What I'm going to do in my 84 is I want to store that value. We're going to need it. So I do second calc, I hit X, store, and then I'm going to call that variable A. And on my calculator, I now have on the screen that A is -0.60477. Great. Well, let's see. Another intersection point I need is going to be over here. That is when the exponential and the arc cosine intersect. Let's call that B, and let's go and get that value off the calculator. Again, we're going to go to the graph, second calc. I want an intersection. I want the intersection for arc cosine, and this time it's the exponential, and I have -0.2607. So B is -0.2607 and a little bit more. I'm going to go back to the home screen, X, store, alpha, B. Great. Last intersection point I'm interested in is over here. That's going to be the last one to define my region. So to find that value, we have the intersection of the parabola and arc cosine. So second calc, intersect. We need the parabola. We need arc cosine. And that one didn't work. Okay, so we'll try that again. Intersection. I need the parabola. There it is. I need the arc cosine. There it is. Oh, I know why. I need to set my guess so I'm over here. Last time, I know this was going to work. Parabola. Move my guess a little bit closer to that intersection point. And I'm getting 0.54699. So C is approximately 0.54699. Well, how do I find the area? If I want the area between two curves, what I'm going to do is I'm going to do an integral. And let's see, from intersection point A to B, that's the integral that I want to do. If I want the area between the two curves from A to B, I have to determine what are my two curves. Well, from A to B, I can see that the top curve is h of x. That is the exponential. The bottom curve is the parabola. So So from A to B, if I want to find that area, it's going to be the h of x minus the bottom one, that's the parabola g of x, and I'm going to integrate that with respect to x. Whenever you're finding the area bounded between two curves, we want to do top minus bottom. The top function is h of x, the bottom function is g of x, that's great. Plus, I need to integrate to find this other area. We're going to go from b to c. Well, which function's on top? Now, it's the arc cosine that's on top. So f of x minus the function that's on the bottom is g of x. I want to integrate that difference with respect to x. And that's it. That was a pretty difficult problem for us to jump into on the first one. But it's most important to keep in mind when you're doing area, it's always top minus bottom from one endpoint to another. And because we had three different curves coming together, we needed to look at the different regions to see over here in this first region, it's the light blue graph that's on top with the parabola on the bottom, but in the second region, it's the arc cosine on top with the parabola on the bottom. Since this was a setup-only question, I don't need to go any further, but I could find this area using Math 9 on the TI-84. That gets you that fn int command. And I would just type in fn int. H of x is what I typed in for y3. G of x is what I typed in for y2. I want to integrate with respect to x. And I'm going to start at A and I'm going to end at B. That would give me some numerical value that represents the area, that represents this definite integral. And I would do a similar integral over here, except I would integrate and it would be y1 minus y2 with respect to x, starting at B, ending at C. Done. All right, so after we spend a day or two working on area, we start looking at volume. We want to imagine this region here spinning around the x-axis. And that's always going to be given to you in the problem. If the problem doesn't state specifically what you're revolving it around, you want to read it again because that information has to be there somewhere. So picture this region, if you can, this semicircle getting revolved around the x-axis. And I usually draw a little kind of like a rotating arrowhead to say how I'm spinning it. So if I take this semicircle and I spin it, what I'm going to get is actually a sphere. Since that's a solid object, the setup is going to be for volume, and it's the same setup all the time for volume. It's going to be pi. We're integrating from some point to some point, whatever our function is squared dx. Right now, for the purposes of this video, I'm not going to go through the whole explanation of where does this formula come from. Maybe at some point later on I'll create another video. But what I care about right now is this is the region. We're spinning it around the x-axis. Because it's a solid object, the volume formula is pi, integral from one endpoint to another, the function squared dx. Well, let's see. They gave me the function. Great. I'm going to integrate from some point to some point. Square root 16 minus x squared squared dx. Well, what are the endpoints? The endpoints are the roots. So we'll call this A, and we'll call that B. Maybe I'm tempted to eyeball those points off of the graph, but let's be really careful with this. If those are the x-intercepts, I'm going to take the square root of 16 minus x squared and set that equal to 0. In order to solve this for x, we can square both sides. Square both sides, we get 16 minus x squared is equal to 0. If I rewrite this, I get x squared equals 16, and so I can find that x is plus or minus 4. A is negative 4, B is positive 4. That means my limits of integration will be going pi times the integral from negative 4 to 4 of the square root of 16 minus x squared squared. The square root and the square would cancel out. leaving me 16 minus x squared. I need to integrate that with respect to x. I'm assuming your integration skills are strong, so we're going to go pretty quickly here. The integral of 16 is 16x minus the integral of x squared is x cubed over 3. We evaluate between negative 4 and 4. So pi, plug in the 4, 16 times 4 is 64. Minus 4 cubed is 64 over 3. Minus pi, now we evaluate at negative 4. 16 times negative 4 is negative 64. Minus negative 4 cubed divided by 3 is negative 64 thirds. Because you have all numbers here, if it's the free response part of the test, you can stop. Let's assume that this is not the free response part of the test and we are being challenged to go further. Well, I would want to get a common denominator. So I'm going to have pi 192 over 3 minus 64 thirds minus pi negative 192 thirds plus 64 thirds. I'm going to have pi 192 minus 64 is 128 over 3 minus pi negative 192 plus 64 is 128 over 3. That's equivalent to 128 pi over 3 plus 128 pi over 3. So that's 256 pi over 3. That represents our volume. Now, if you're a strong geometry student, you might recall from geometry that the volume of a sphere is always 4/3 times pi times the radius cubed. Because this region is a semicircle and we're revolving it around the x-axis, we're generating a sphere. For this problem specifically, the radius is 4. So if I use my geometry knowledge, we have volume is 4/3 times pi times 4 cubed. 4 cubed is 64. 4/3 times 64 would indeed give you 256 pi over 3. I don't know about you, but that just makes me happy. It makes me happy to know that all of this beautiful calculus work that we just did, first of all, that it's correct. This also makes me happy because this volume formula that I've always just assumed to be true, my geometry teacher, Ms. Dabowski, in high school taught me that formula. I use it all the time. And it's nice to know that it actually works. I'm getting the same answer using two very different techniques. This is the kind of stuff I find exciting. What is very powerful, though, about the calculus is we can do all of this beautiful calculus here even if we don't have a nice simple object like a semicircle. So let's move on. This next problem, we have the region bounded by g of x equals e to the x. So this guy over here is exponential e to the x, and the line y equals 4. So that's this in the first quadrant, and we're revolving it around the x-axis. My advice to my calculus students always is let's actually make sure that you know what we're looking at, what the region is. I only see one space that is bounded by e to the x, y equals 4, that's in the first quadrant. That's this region over here. Okay. And I don't necessarily know what name we want to give that, but this is the region. And we want to revolve it around the x-axis. Again, my little swirly there to indicate we're revolving it around the x-axis. Okay, now what's different is that when this object spins around the x-axis, you might have a hard time visualizing that. You're not going to get a solid object. You're going to get something that's hollow. I'm going to attempt to draw it, but I'm not gifted in the drawing skills at all. So let's see what I can do here. It looks to me like the object looks something like this. Yep, now I have evidence. I've told everyone on the planet that I really can't draw. When I revolve that region around the x-axis, I'm going to get something like that. I've got this region up here, it's spinning, but I've got this part in the middle where it's empty. There's a hole there. This is when we start to think, all right, I have a hollow shape. If I were to slice this shape, I'm going to get regions that are washers. And normally I have a washer handy, and sadly I don't. Okay, by a washer, I just like to think of a donut, like Homer Simpson. Donuts. If I wanted to find the area for that donut, well, it's a big circle with a small circle. I'd find the area, which is pi big R squared minus pi little r squared. The big radius starts at the center and goes out to the outer shell. The small radius starts in the center, goes to the inner shell, and the area is just pi big R squared minus little r squared. For this particular problem, we have volume, so pi. We're doing an integral. Let's see, I know I'm going to start at 0. I don't necessarily know exactly what that endpoint is yet. Don't worry, we're going to go and figure that out. If I'm spinning this light blue region around the x-axis, in order to figure out big R, you start at the x-axis and you go until you hit the outer shell. Normally, someone in my class, once I hit the line y equals 4, would yell, stop. That tells me the big radius is going to be 4 units long. Anywhere I draw this little representative slice, the radius is going to be 4. If I want to find the smaller radius, I start on the x-axis. Someone yells stop. I stop right there. The little radius is e to the x. So my volume setup is big R squared minus little r squared, and then integrate that with respect to x. The only thing we're missing is our limit of integration. We need to know what that a value is. Well, where does a come from? A comes from the intersection of the exponential e to the x and y equals 4. So I can say, all right, if I want to get a, I set e to the x equal to 4. I take the natural log on both sides. Natural log of e to the x equal to natural log of 4. The natural log of e to the x, I can bring the x down in front. And since the natural log of e is known to be 1, x is the natural log of 4. So my volume is actually going to be pi. We integrate from 0 to natural log of 4. 4 squared is 16. E to the x squared means e to the x times e to the x. That's e to the 2x dx. I want to perform the integration. So here's pi. Integral of 16 is 16x. Minus the integral of e to the 2x will be e to the 2x times 1/2. We then evaluate this from 0 to the natural log of 4. Plug in the natural log of 4 first. 16 natural log of 4 minus 1/2 e to the 2 times the natural log of 4 minus pi, evaluate at 0. And let's be careful. 16 times 0 is 0 minus 1/2 e to the 0 power. Since e to the 0 is 1, we have 0 minus 1/2. I see a lot of calculus students just think that this term over here is always equal to 0. No, not in this case. Let's see. Do we need to go any further? Well, it always depends. If it's free response, this is where we stop. If not, let's see. What else could we do? We have 16 natural log of 4. I'm going to leave that. Up here, we have e to the 2 ln of 4 power. And I'm tempted to cancel out the e and the natural log. Unfortunately, I don't have the e and the natural log right next to each other in the way that I need them to be. However, I do have a property of logs that allows me to bring powers down in front. We saw that used over here when we were solving the exponential equation. So I can actually use that property to my advantage and raise the 2. So I now have, I can rewrite 1/2 e to the natural log of 4 squared, which is 16, minus pi. 0 minus 1/2 is negative 1/2. All right, let's keep going. Pi, 16 times the natural log of 4. I don't think there's much I can do there. E raised to the natural log of 16. The e and the ln cancel out, leaving me minus 1/2 times 16. Negative pi times negative 1/2 is the same as pi over 2. So I think we're about there. We have 16 pi natural log of 4. 1/2 of 16 is 8. So minus 8 pi plus pi over 2. Whew! Nice and colorful. I love being a math teacher. Anyway, that's the final answer. Big takeaway from this, where I see a lot of my students struggling. Once they've identified the region, you absolutely must spend some time determining, is the region, is the solid, is it going to be hollow or is it going to truly be solid? If your shape is hollow, then you're always going to be using volume equals pi, integrate from one endpoint to another, big radius squared minus small radius squared. Let's move on. Let's try another one. All right, so we've got the region bounded by the curve f of x equals the square root of x, g of x equals negative x plus 6, and the x-axis is revolved around the x-axis. So the region this time is over here. Square root of x, I know what that looks like. G of x, great. Okay. Depending on where you are in the course, I might not give you this diagram. I might expect, since these are functions that are well-known functions, you can generate it. But for now, let's do this. I'm revolving around the x-axis. Great. Revolving around the x-axis is usually easier. I want to take this shape and I want to spin it. And let's see, is it hollow or solid? I see this entire region touches the x-axis. That's what I'm spinning it around. So I have a solid object. Great. Solid objects. I normally just have pi times the integral from a to b. My function squared dx. Okay. So there's a problem here, and the problem is that depending on where I am on my journey from one root to the next root, I don't always have the same function on top, right? At this intersection point, I'm going to call that A, we switch functions. From 0 to A, the square root of x is on the top. From A to, for now, let's call this B, g of x is on top. So that means to me I'm going to need 2 different integrals. So I'm going to have volume is equal to pi. We know 0. Let's see, we have to go to A. The function is the square root of x. That's what gets squared. We integrate with respect to x. That volume will give me the volume when region 1 is revolved around the x-axis. Now I need to look over here at region number 2. Region number 2, that volume, we're going to have pi, an integral from A to B. The function is negative x plus 6, the whole thing squared, and we integrate with respect to x. It's a beautiful setup. You're going to move in the right direction, but we have to determine the values for A and B. Well, let's start with the value for B. That one's pretty easy. What makes B so special? B is the x-intercept for negative x plus 6. And so I can see right away that x equals 6, so B is equal to 6. Now what makes A so special? A is the intersection for the square root of x and negative x plus 6. With a little bit of algebraic manipulation, I'm going to square the left, I'm going to square the right. Square root of x squared is x. Negative x plus 6 times negative x plus 6. X squared negative 12x plus 36. I see that this is quadratic, so I'm going to rewrite it as x squared minus 13x plus 36 is 0. I can factor, so I have x minus 4 times x minus 9 is 0. And I can solve this to get that x equals 4 or x equals 9. So it looks to me like we'd actually have two intersection points. When you go back, you can, if you know that this is 6 and the intersection point happens before 6, 9 doesn't make sense. If you go back, and actually the proper way to do this, you would check to see, will 9 satisfy the original equation? Square root of 9 is 3, but negative 9 plus 6 is negative 3. No, that doesn't work. That's an extraneous root, or an extraneous solution. So A is equal to 4. So what does that mean? That means I can go back to my integration problem. And we have pi. We're going to integrate from 0 to 4, square root of x squared dx, plus pi. We're going to integrate from 4 to 6, negative x plus squared the whole thing dx. Let's pick up the pace now. This should be much easier. We have pi. Integral from 0 to 4, square root of x, the whole thing squared is just x dx. Plus pi, integral from 4 to 6. Negative x plus 6 squared. We already did that. That's x squared minus 12x plus 36 dx. Okay, I come back over here. The integral of x is x squared over 2. So I evaluate that from 0 to 4. Plus pi, integral of x squared, x cubed over 3, minus the integral of 12x, 6x squared, integral of 36, 36x. Evaluate between 4 and 6. Okay, we have pi, long problems. 4 squared is 16, 16 over 2 is 8, minus 0, plus pi, plug in the 6, 6 cubed is 216 divided by 3, 72, minus, plug in 6, 6 squared is 36 times that, 216, plus 36 times 6, 216. Oh, bad planning on my part. Minus, we still have a pi in front here. Plug in 4. 4 cubed, we have 64 over 3. Minus 4 squared is 16 times 6, 96. Plus 36 times 4 is 144. Okay, we're going to finish this off. 8 minus 0 is 8, so this first part is 8 pi. The second term, negative 216, positive 216, those cancel. We get 72 pi minus pi. What happens in here? Negative 96 plus 144 is 48, so we're going to get 64 over 3 plus 48. I can combine the 8 pi and the 72 pi to be 80 pi minus pi. Get a common denominator. I think you're going to have 64 over 3, and let's see, 48 is the same as 144 over 3, so 208 thirds. If you really are just committed to getting the most simplified answer possible, I believe 32 pi over 3 is your final answer. My advice to you always, especially if it's the free response section, stop as soon as you hit all numbers, which for me is right here. I would not spend any time after the part that I've just bubbled in orange. All you're doing is running the risk of losing valuable points that you need. So let's not throw them away. All right. One more. One more question in terms of horizontal revolution. This one is calculator active, so let's get your calculator out. And this one is going to be a little bit different for us, and it's different in a very important way. We have the region R bounded by f of x in the first quadrant, revolved around the line y equals negative 3. Y equals negative 3 is down there. This region, this gray region, we only want the part bounded by x sine of x in the first quadrant. So we only want this part here revolved around y equals negative 3. I can see I've got this piece that's missing. So I know right away the shape is hollow. Because it's hollow, we have pi, it's going to be an integral from a to b, big radius squared minus the small radius squared, and integrating with respect to x. In order to get the large radius, big R, we have to figure out where do we start. We start at the axis of rotation, which is y equals -3. And if I start here and I go up, somebody else stop, there's big R. Little r would go from here to that little line. Little r is pretty easy. How far is it from the line y equals -3 to the x-axis? Well, that's just 3 spaces. In order to get big R, you have to think, how far is it from y equals -3 up to the curve y equals x sine x? Usually with my calculus class, we talk about top minus bottom. So big R is x sine x minus -3. Of course, that's the same as x sine x plus 3. So my volume expression will be pi, integral from a to b. You still have to figure out those endpoints. Big R, x sine of x plus 3 squared minus little r, 3 squared dx. We need our limits of integration, and this is where you're going to need your calculator. So if I graph x sine x, alright, so we're going to graph x sine x, and right, now I need to find the roots that I'm interested in, so let me change my window just a little bit. Okay, I hope you're doing this along with me at home or wherever you're watching. Okay, the root that I'm interested in is the one that's over here, so second calc 0, I need a left bound, I need a right bound, here comes my right bound, and then I need a guess, and I'm going to call that point A. According to my calculator, A is about 3.1415927. That's actually pi, but I'm going to use the store feature. So I'm going to go back to the home screen and hit X, store alpha A. A is now locked in. My other endpoint is over here at 0. So my volume is going to be pi, integral from 0. It's kind of unfortunate, I apologize. I had A and B as my original limits of integration, but I've now referred to this intersection point over here as A. I apologize for the double use of A, especially since I'm using it in different places. What I mean by A is, where do I start the integration? By B, where do I end the integration? Well, I start at 0 and I end at my other variable, A. So 0 to A. X sine of x plus 3 squared minus 9 dx. Thankfully, this is a calculator active question. So I'm on the home screen, and my keystrokes are going to be Math 9, again on the TI-84. Now, I can type in the function x sine x plus 3. Because I have to square the whole thing, I put in parentheses to begin with. Minus 9, integrate with respect to x, starting at 0, ending at A. On my calculator, I'm getting 23.2318. So I'm getting 23.23187054. Now be careful, that number accounts for the integral. It does not include the pi, so I have to write the pi. Or I can just say, all right, well, let me multiply that answer by pi, and I get that that is approximately 72.9850731. Either of these two answers is perfect. Make sure you use the approximate symbol. Since we're doing this on the calculator, we are doing some estimation here, and it's important to acknowledge that. All right, I think that is the last problem where we're doing a horizontal revolution. And now we're going to start spinning vertically. And that requires a slight change. We only have 3 more problems that we're going to do with the time allowed, and then I'll record a second video later on. All right, region bounded by e to the x. We've already seen this one before. So here's g of x equals e to the x, and the line y equals 4. First quadrant, okay, there it is. I'm revolving this shape around the y-axis. So stop for a second. Think about this little piece in here that I've now shaded in pink and purple, and I'm spinning it around the x-axis. Right? Maybe, gosh, I'm trying to think of a candy that looks like. I can't think of the name of it right now. I think they're called drops, maybe. What you would get, again, I'm not a very good artist, you're going to get something that kind of has that shape, almost like an acorn with a flat top. What makes it different is when you're spinning around a y-axis or something that's vertical, the big radius, your small radius, we actually have them going horizontal, parallel to the x-axis. So let's see, we have a solid. My volume setup is almost the same. It's going to be pi. We're going to have an integral. We're going to have something, we're going to have our radius squared. But since we are revolving around the y-axis, because my slices are now parallel to the x-axis, it's a dy integral. So we need y values for the lower limit, y values for the upper limit. Our function in here has to be in terms of y. So what that means is we're going to take the equation y equals e to the x and rewrite it in x equals form. To do that, we'll take the natural log on both sides like we did before, and we get x is equal to the natural log of y. That is the other way to write this curve over here. Y equals e to the x is the same thing as x equals the natural log of y. X equals the natural log of y is what creates this outer shell, so my volume will be pi natural log of y squared dy. Where am I integrating from? Well, I need y values. This is why I normally write y equals and y equals here. Let's see, where is this point? What I know for sure is the x-coordinate is 0. Since we're looking at the function e to the x, I know e to the 0 is 1. So the lower limit of integration is y equals 1. The upper limit of integration, well, that's this point over here. And since this point is the intersection of e to the x and y equals 4, I know the y value is equal to 4. I don't know what the x value is, and honestly, because this is a dy integral, I don't even care. And so we would integrate this function from 1 to 4. Now, what I didn't think about before when I selected this problem is how do you actually integrate this? This would have to be either a question where you're asked to just set up the integral. So that's one option. The other is that it would have to be a calculator active question. Okay? I didn't indicate either of those in the original prompt, so I'll have to revise that at some point. But from here, I would just pass it over to my calculator. Integrating the expression natural log of y, the whole thing squared, is possible. It can certainly be done, but it goes beyond the scope of a Calculus 1 course. This is something that we'll be attempting next year in the Calculus BC program. All right, let's keep going here. New problem. The region in the first quadrant bounded by, oh, I didn't even give you the graph this time, by the x-axis and y equals x squared. So let's see, y equals x squared I know is a parabola. There we are. From x equals 0 is a vertical line. X equals 4 is another vertical line. Now we're rotating about the line x equals 4. Another example of a vertical rotation. Well, let's start. That's our region. So there's a bit over here that I've shaded in black. We're revolving that around x equals 4. Maybe it's kind of like a Hershey's Kiss for you when you think about the shape. Let's see, this is solid. We love solids. Those tend to be easier. Pi, we're going to have an integral. We're going to have something getting squared because it's a vertical rotation, dy, from y equals something to y equals something. Well, let's see. What can we do pretty quickly? If this is the region, the lower limit would be right over here. I know that this is the point 4 comma 0. Since it's a dy integral, I only want the y value, so y is going to be 0. I'm going to stop the integration over here at this point. This point is the intersection of x equals 4 with y equals x squared. So that's the point 4 comma 16. So I'm going to integrate from 0 to 16. Great. I still need to figure out what's the radius. How far at any slice, if I'm just going straight across this little region and it's hard to see, well, where do I start? I start, instead of y equals x squared, we're going to write this as x equals the square root of y. I end at the line x equals 4. The distance between these 2 points, no matter where I am on this region, is going to be 4 minus the square root of y. So that's how long the slices are. I'm always going from one side over to the other. Okay, I think we've got all the information that we need. With pi, we're integrating from 0 to 16. 4 minus the square root of y squared dy. I want to integrate this, so let's do it. Pi, 0 to 16. 4 minus the square root of y times 4 minus the square root of y dy. Most people are probably going to choose to do the box. I'm just going to multiply it out in my head. 4 times 4 is 16. 4 times negative square root of y is negative 4 square roots of y. Another negative 4 square roots of y brings me negative 8 square roots of y. Negative square root of y times negative square root of y is plus y. Integrate that with respect to y. In order for me to do that, I want to get everything in integration ready form. So we'll make this 16 minus 8, I'm going to say y to the 1/2 plus y dy. The integral of 16 is 16y minus 8y to the 1/2. Add 1 to the power. Makes it y to the 3/2. Divide 8 by that new power. 8 divided by 3/2 is the same as 8 times 2/3. So 16 over 3. Plus, add 1 to the power. Y squared. Divide by the new power. It's the same thing as multiplying by 1/2. Evaluate at 0 and 16. So here's pi. 16 times 16 minus 16/3 times 16 to the 3/2 plus 1/2, 16 squared, minus pi, evaluate at 0. 16 times 0, 0, minus 16/3, 0 to the 3/2, 0, plus 1/2, 0 squared, 0. Great. And let's assume we're on the multiple choice. 16 times 16, 256, minus 16/3. 16 to the 3/2. Take the square root of 16, that's 4. 4 cubed is 64. Ugh. Plus 16 squared, 256, times 1/2. 128. That's all 0. Don't worry about it. Let's get a common denominator. I see a third here. 256 is the same as 768 over 3. Minus 16 times 64 is 1024 over 3. Plus 128 is the same as 384 over 3. Good golly. Feel free to use a calculator if you need to. 768 plus 384 is, what is that? 768 plus 384. And then you're going to subtract from that 1024. I'm getting 128 over 3. So final answer of 128 pi over 3. Some ugly numbers here at the end. That I wouldn't expect to see this on the no calculator part of the test. I'd expect to see it on the calculator active section. You never know, but I don't think the AP folks are really all that interested in our ability to do 256 minus 16 thirds times 64 plus 128. That's not something we're focusing on in calculus. That's stuff you should have been able to do coming out of 4th grade. All right, here comes the last one before we wrap up this part of the video. The second video is going to involve solids that have known cross sections. But let's go through this one. We want to find the volume of the solid of revolution generated when the region in the first quadrant enclosed by the graph x equals y squared and x equals 2y is revolved about the y-axis. Again, no graph is given. Depending on your comfort level with pre-calculus, you know x equals y squared is a sideways parabola. And so you would pretty quickly generate something that looks like that. If you don't know that, well, let's get this into y equals form. I can take a square root on both sides. That means I'm going to have y equals plus or minus the square root of x. The top part is positive square root of x. The bottom part, negative square root of x. X equals 2y, well that's just a line. Specifically that's the line y equals 1/2 x. So there it is. That's the region in question. What are we doing with this region? We're spinning it around the y-axis. Okay? When I do that, I take this little leaf-looking shape, I spin that around the y-axis. What that's going to generate is a hollow object. Okay? Because it's hollow, we know it's pi. There's going to be an integral from some point to some point. Big R squared minus little r squared, but it's a dy integral. To find big R, we start here on the y-axis and we go across until we hit the outside curve, and that's the line. To find little r, we start on the axis of rotation and we go until we hit the inside curve. That's y equals the square root of x. Big R, well, we're going to start on the line, which we said is x equals 2y. It's going to be right minus left, so 2y minus 0. Big R then is 2y. Little r, we start at x equals y squared, that's this curve, minus 0. So my integral becomes 2y, the whole thing squared, minus y squared squared dy. My limits of integration, I start down here at the origin, which is 0, 0. I go up here to this point. Unfortunately, we haven't actually figured out what the coordinates are for this point, so we're going to have to do the work. Let's see, what do we know? We know that x equals y squared, and we know that x equals 2y. So how about if I say y squared is equal to 2y? I can bring the 2y over. Y squared minus 2y is 0. Factor out the y. So we get y is equal to 0 or y is equal to 2. At this point right here, that intersection point, the y value is equal to 2. That means I'm going to integrate from 0 to 2. We have pi, integral from 0 to 2. 2y, the whole thing squared, is 4y squared. Y squared squared is y to the 4th. dy. Integrate each of these. Pi, integral of 4y squared is 4y cubed over 3. Minus the integral of y to the 4th is y to the 5th over 5. Evaluate between 0 and 2. If pi, 4 times 2 cubed over 3, minus 2 to the 5th over 5, sorry, that's sloppy, 2 to the 5th over 5, minus 4, 0 minus 0. 2 cubed is 8, times 4 is 32. We have pi, 32 over 3. 2 to the 5th is also 32. 32 over 5. Let's finish this off. We need a common denominator, which will be 15. Multiply by 5 over 5, 160 over 15. Over here, multiply by 3 over 3, you get 96 over 15. Your final answer, 160 minus 96 is 64 over 15. Don't forget the pi. Woo! That's it. There is some great stuff happening here. I would highly encourage you to take your time and maybe go back, watch the video when you have some time. Before you actually follow along with my solution, look at the setup. Are you able to generate the same integral? If you are able to generate the same integral, go through, actually see how much of this you can do without referring back to the video. This should be great preparation. Just looking at the video now, I realized the one bit that I didn't cover, and maybe we can improvise a little bit, is sometimes you want to take a region, whatever that region might be, and you want to revolve it around a vertical line, like for example, y equals negative 3. Hello? How about x equals negative 3? You want to revolve that region around a vertical line that is not the y-axis. So in order to do that, you're going to, when you do your big R, you start right over here and you go all the way across to the outer shell. There's big R. Little r, you would go right from there until the y-axis, if that's the boundary. Now, I did kind of improvise this. I picked a region that when you spin it around x equals negative 3, you actually are going to have to split the region. We have this intersection point here. And at that intersection point, the outer function changes. So we have below that line is region number 1. Above that line is region number 2. You'd have two different integrals. You'd have two different expressions for big R and little r. You'd start at this intersection point with your integration, and at that intersection point for region 1. You'd add on to it this intersection point up to that intersection point for region 2. Both regions are hollow, so you're going to use big R squared minus little r squared in both. Anyway, if I ever reshoot this video, I will be sure to include an example like that. But this should be enough. And I wish you guys all the best. Later on today, I'll be recording a video on what do we do when we're not revolving regions, but instead we know these regions are the base of a solid, and we know more about the cross sections. Until then, have a great day. Good luck in the exam.